Well, okay. Welcome everybody. Is this on? Yeah, right. It is my pleasure to so formally I am the colloquium organizer, but I should say Gonzalo invited the speaker for today and is organizing the visit. So it's my pleasure though to introduce David Woolpert from the Santa Fe Institute, among other affiliations, which I'll mention in a minute. So David got his PhD, if I understand this right, from the University of California in Santa Barbara, and is now a professor at the Santa Fe Institute in New Mexico. And he is also an external professor and staff member at various other institutions, including the Complexity Hub in Vienna, ICTP in Trieste, and Arizona State University. And he, along his career, worked at many distinguished institutions, including the Los Alamos National Lab, Max Planck Institute in Germany, in Stanford, at NASA Research Center, at Rockefeller University, and at IBM, just to list a few, and the list goes on. He's the author of 3 books and 3 patents. He has won many distinguished awards and prizes, including a fellowship of IEEE. And his research topics include the thermodynamics of computation, foundations of physics, the dynamics of social organizations, machine learning, game theory, and distributed optimization. And today he's going to talk about extending computational complexity theory to include thermodynamic resource costs.
Okay, thank you very much. It's great to be here. Thanks everybody for coming. So physicists have been interested in the relationship between computation, information processing, or generally speaking, and physics at a fundamental level, arguably all the way back to Maxwell and his eponymous demons. Then through the 20th century, John Wheeler with it from bit. People wanted, and Stephen Wolfram still is trying to pursue that line of work where somehow you formulate all of physical reality, all of physics, as being emergent from a simple computational process to try to understand the relation between physics and computation. Some of the first really solid results along these lines came in the mid-20th century with people like Rolf Landauer, Charlie Bennett, Seth Lloyd, Wojciech Zurek, and so on, with their initial work on the thermodynamic cost, as they called it, the thermodynamic price of things like bit erasure. But if you think about the state of statistical physics all the way through the end of the 20th century, all of this was about systems that are either at equilibrium, in a metastable state, or infinitesimally close to an equilibrium. All of spin glass theory, for example, concerns that. And Parisi, with his recent Nobel Prize, it was all about those kinds of systems. So very, very no degrees of freedom that are evolving much more quickly than the other ones, and very close to equilibrium. And that's called complex systems in physics. So everybody here who is very, very close to equilibrium and has no degrees of freedom that are evolving quickly, please raise your hand right now. All of what's called complex systems in condensed matter physics, none of it is what everybody else would call a complex system. None of it is the interesting stuff. In hindsight, it's actually amazing how people like Parisi and so on managed to extract so much powerful insight from such a broken foundation. Okay, now Parisi won a Nobel Prize. Other people, Rolf Landauer and Charlie Bennett and so on, very important contributions, but they were trying to analyze the thermodynamics of things that are intrinsically far from equilibrium, computers. Statistical physics, the tools they had to use at the time, did not apply. They were broken. As a result, if you, for example, go back to Rolf's 1961 paper, where he started all, you will notice that there's no actual equations, except for he just sort of says KT log 2, and then goes through some toy examples. None of it's derived. Not surprisingly, there are then lots of arguments about it, and sort of that's the way that things work. Okay, then starts the 21st century. And here the cavalry comes from over the hills, and we hear the trumpets, do-do-do-do-do. People started to, very, very brilliant people started to actually develop what's now called stochastic thermodynamics, non-equilibrium statistical physics. This applies to systems that are arbitrarily far from equilibrium, that are evolving like arbitrarily quickly. In other words, it applies to computers. Let me first give a simple example of its power before getting on to the specific topic that I'm going to be talking about today about applying stochastic thermodynamics, fully formal statistical physics, to computer science, to the system that are of interest into computers, and just how amazingly rich this is. Just so much is falling out of the sky. So here's a gorilla, proverbial 800-kilogram gorilla that was in the room of statistical physics all the way through the end of the 20th century that nobody even talked about, never mind tried to resolve. On our scale, we evolve according to the second law. If you run a movie of what's going on in this room forwards and backwards and give it to somebody else, they can always tell which is forward or backward. Microscopically, of course, you could not tell which direction the movie is going. Microscopic laws of physics are time symmetric. So the obvious question, oh, that's much better. Okay, better? Okay, were people not hearing me before? Oh. Okay, so I should not repeat, I assume everybody went through, okay, yeah. To give just one simple example, macrodynamically, the second law applies and there's time asymmetry, and you can always tell if a system is evolving forward or backward, microscopically not. It's now generally understood that the way that you can actually have both of those, a resolution of Loschmidt's paradox, is based upon the fact that the Big Bang is now past. So ultimately, the fact that time seems to go forward to you personally proves that there was a Big Bang 13 billion years ago. But anyway, so here's the obvious question, the huge question that nobody even asked. If that's true at the micro and the micro scales, what about the intermediate mesoscales? The second law must sort of hold at that level. I can often tell if the movie's going forward or backward, but not always. Is that the case or not? Describe the actual physics of the arrow of time at those intermediate scales. Nobody had even thought to ask the question. Stochastic thermodynamics provides the answer. These are what are called the fluctuation theorems. It is now known that what's going on is there's an actual distribution over possible changes in the value of the entropy of a system. The average of it cannot go down, the average of that distribution. So expected entropy cannot go down. But individual instances, individual samples, it can go down. And as you move to smaller and smaller systems, the probability that the entropy decreases grows and grows and grows. This has been experimentally verified. It's got nothing to do with the precise topic I'll be presenting today, but that's just one example of the strength that this new formalism is providing us. Okay. Unfortunately, my great preamble was not being recorded, but there you go. On to the subject of today's paper. This is with many collaborators. I'm working now with Gonzalo and Edgar Roldan on another set of multiple papers that we'll be adding to this list. But these ones, at least you can find them all on archive. So there are many different ways of formulating stochastic thermodynamics. Some of them actually, what they amount to is that stochastic thermodynamics is identical to open quantum thermodynamics, just in the classical rather than quantum regime. But that's not what I'll be talking about here. For simplicity, I'm going to assume we've got just a countable state space and the simplest possible dynamical process of probability distributions across that state space. It's linear. The derivative of the probability of state I with respect to time is just given by a linear function of its current probabilities. In other words, a master equation. In general, we can allow the rate matrix to evolve with time. Okay. And here are some examples that you can describe with this: the dynamics of a digital gate in a circuit. There's been some great work by Jean Davant, Massimiliano Esposito, and Noel Freitas on PRX on this recently. Dynamics of an entire digital circuit. This is some other work I'm doing with Gulje Kardesh, dynamics of deterministic finite automaton. This is, well, we're not actually restricted to CTMCs with any of it now that I think about it, continuous time Markov chains. But an example of that can be described this way is the work with Gonzalo and Edgar, and dynamics of a Turing machine. So these are some examples of systems you can model this way. Note, by the way, that many financial markets, ecosystems, social systems, and so on, you can also model this way, and very often they are. So a lot of the theorems in stochastic thermodynamics actually apply to those kinds of systems as well. Nobody's investigated it. Yep. Sure. If you're naively saying that I've got not an infinite heat bath, but a finite one. So this is in the quantum regime, that's quantum open thermodynamics. That is not describable as a non-Markovian dynamics, because as you evolve through the past, you are changing the state of that finite bath. Since it's finite, that information is not being lost. It's not an infinite bath, it's a finite one. Therefore, the interaction that you have now with that bath will tell you something about the past. Or to view it another way, your past state is telling you something about your dynamics now. Stochastic thermodynamics can still apply in that to those kinds of systems. It's called inclusive Hamiltonian. But that is not actually a continuous time Markov chain. It's inherently non-Markovian. And actually, I've got one, my paper with Jan Korbel, my second collaborator. We've got one that where was it? May have been New Journal of Physics, I forget, where we investigated some ways of trying to just assume that you've got non-Markovian dynamics without specifically saying a finite bath. So anyway, so people have been investigating continuous time Markov chains for, I don't know, at least a century. Fokker-Planck dynamics, so it must be a century and a half or so. Fokker-Planck is this, just in continuous state spaces. People have been investigating information Shannon entropy, well, at least since Shannon, 75 years ago or so. But of course, also even down all the way to Gibbs. This is another huge gorilla in the room. Nobody had thought to ask the very simple question. This was not a homework problem to anybody. Well, let's say that your underlying system evolves according to a continuous time Markov chain. What's the induced dynamics of the entropy of the states of the system? Could imagine that that's a good final exam question to give to your students, and actually it is. You can spend about a page of algebra or so, and this is the result. It divides into a sum of two different terms. The first one is called in the literature, for reasons that I'll get to in a second, the entropy flow. The second one's called the entropy production. They're actually identical if you look at the definitions, except for this one's got a ratio of p's inside the logarithm that the first one doesn't. And it's that ratio of p's, which when you multiply it times this, the kp, which is just really the derivative of p with respect to time, what you're going to be getting is the derivative of p with respect to time times the log of p. So that's a very, very quick reasonableness argument about how you can actually just do this. Here's the crucial thing that I'll be saying in a second. This is, in a certain sense, a proof of the second law for continuous time Markov chains. EP, we'll take a couple of lines of algebra where you can prove this is actually never, ever less than or equal to 0. Okay, given that it's never less than 0, let's just do the obvious naive thing, integrate this equation over time. What you get is, here in essence, I'm defining that the Shannon entropy flow from the system, leaving the system, is equal to the sum of the total entropy production between your beginning and your ending times, minus the entropy gains, or in other words, plus the drop in entropy. Fundamental, okay? And you can, to get to the question from in the audience, this also, you can get the exact same equation in cases of a finite path, non-Markovian dynamics, the same equation comes out. So the first thing that gives you, it's what's now called the generalized Landauer bound. Let's say your system is connected to multiple heat reservoirs. Okay. So first of all, what I presented so far, that's just math. That's just algebra. There's no physics yet. The physics comes in, you're going to make an assumption that's formally called local detail balance. It means microscopic reversibility. And that allows you to identify aspects of the rate matrix with the system being coupled to different thermal reservoirs. That's how the physics comes in. So let's say the system is connected to multiple reservoirs, for example, heat baths at different temperatures, so KT is not even defined. Allow an arbitrary number of states, an arbitrary initial distribution, get this out of the way, and an arbitrary discrete time dynamics. Then let's just apply our formula to this kind of a situation. Because entropy production is non-negative, we get this result. Negative delta Q is greater than or equal to the drop of entropy. So in particular, if we say that there's a single heat bath at a temperature T, then you can actually identify the heat flow in the formal sense is equal to KT times delta S. Two possible states, P0 is uniform, process implements bit erasure, assume local detail balance, that's the condition I mentioned before. So the generalized Landauer's bound, because EP, this is the generalized Landauer's bound, it follows from the fact that delta sigma is greater than or equal to 0. The generalized Landauer bound tells us the total heat flow into the environment is greater than or equal to KT times the drop in entropy. The drop in entropy, if I'm taking two possible states where they're initially uniform and I'm just doing bit erasure, well, the drop in entropy, the initial entropy for a bit that can be up or down is log 2. The ending entropy, if I've got a delta function, the entropy of a delta function is 0. Log 2 minus 0 is 0. So the total heat flow into the environment is greater than or equal to KT log 2. That was Landauer's original bound that he derived semi-formally, that he thought applied even to these kinds of situations, which it doesn't. Okay, and here are some great references. Parando, this is a nice review article. Takahiro Sagawa. This is a very important article for anybody who still thinks what, quote, logical reversibility, end quote, is actually important thermodynamically, and so on and so forth. Okay, so let's see what some of the implications are of what I've presented so far. Very, very simple stuff. What are the implications for actual computers? So let's start by saying a couple of things by the simplest possible model of a computer. First, does anybody know who this is? Yeah, it's Claude Shannon. So it's kind of obligatory. You've got to give photographs that you stolen from the web of the people you refer to. That's kind of people. It illustrates the fact that you're really web savvy. You know how to do this. But anyway, Shannon, he, like people like Kolmogorov, I think that they were not normal humans, that they were either travelers from the future or they were aliens. Those are the only two possibilities. Shannon did many, many things. He formulated all the important questions of information theory and solved the most important ones. He figured out how to ride unicycles and bikes at the same time. He did some very early work on machine learning, actually, teaching little robots to navigate mazes. But he also, and this was in his master's thesis, as I recall, it was either the master's or the PhD. He invented the foundations for the field of what's called Boolean function theory, the mathematics of Boolean circuits. He invented it. So what a Boolean circuit is it's a map. It's things like a digital circuit. It's things like what's going on here. You've got a set of n input bits. You just then go through a bunch of ands, ors, and nots, whatever you wish, and you finally get a single bit at the end. And so those intermediate things are called gates. And so long as the gates form what's called a universal basis, you can actually implement any desired function from b to the n to n with some Boolean circuit. And he proved this. He proved all the results about the actual minimal size of a circuit for implementing a function. And here's an interesting fact. He proved that almost all functions have the property that the minimal size circuit requires more than polynomial number of gates. Nobody's been able to actually generate a single example where they can prove that's true. But he proved that almost everyone must be that way. So there's some really cool stuff in computer science theory. Here's an example of a circuit. I don't remember, these are ands. I guess that's an or. This is maybe ands and or, that's a not. I mean, this might be ors. I don't know. But in any case, this is mapping all strings of 3 bits to a single bit. Okay. And the key thing with a digital circuit, with a Boolean circuit, is that these are restricted in that you are not allowed any branching of the dynamics, and you're not allowed to have feedback. So that's the only restrictions on the actual topology here. So let's just start analyzing the thermodynamics of this. We now have the tools. We can do that. Cool. Let's have fun. The people who invented stochastic thermodynamics, who've been doing all that great work, it's still a very, very young field. As so often happens in science, they are siloed into their little discipline. So the examples they think of are things like stretching RNA back and forth, looking at cell receptors on the walls of cells. What they've got, as I alluded to before, can be applied to financial markets, ecosystems, computers. They have given us a set of tools that is far, far more powerful than they appreciated. But so anyway, advertising aside, here is a particular circuit. Remember our rule about the entropy flow. This is the heat flow out to the heat pipe. This is how hot your device becomes. Let's fix for each. Remember that for a fixed p of x1 given x0, notice that changing the initial distribution for a fixed update function will in general change the generalized Landauer cost. You change P0, you're going to change the entropy of P0. And for a fixed P of x1 given x0, in general, you'll also be changing the entropy of P1. So the very same system with just a different initial distribution, different minimal heat flow. So now take the exact same AND gate, exact same logical AND gate. Notice that its Landauer cost is going to differ depending on where it is in the circuit, because it's going to have different initial distributions. I've got an AND gate. Let's say you've got a distribution over your triplet of input bits. That's going to induce a distribution over the initial states of this AND gate. But it's in general going to induce a different distribution over the initial inputs of this AND gate. And there will be a different one for that gate, and so on. So changing where the exact same gate is in a circuit is going to be changing the minimal heat flow that gate contributes to the heating of your overall device. Okay, well, I can see how maybe that'd be important, but why in particular? The reason it's important is any desired map from inputs to outputs, any Boolean function can actually be implemented by an infinite number of circuits. It's an extremely billions of euros kind of important field to try to actually design the circuits that are optimal by whatever your criteria of optimal is, given that we know the input-output function. This is what has to be figured out before you print circuits in a fab in Taiwan, because it's an infinite set of possible circuits for any function you might want it to do. So because of this factor, though, all of those different circuits that implement any given same function, they're going to have a different total minimal amount of heat flow they generate. So here is an obvious question. Find the for a given input-output function that you want, design the circuit at a given distribution over its inputs, design the circuit that has a minimal total Landauer cost. Okay? It's probably NP hard. We don't know because nobody has done anything on this problem. I've just stated it, and it is stated in other papers, but nobody has actually addressed this. Potentially a huge field. Anybody want new research projects? Here's one. Okay, so that was the simplest possible computational machine that you can find in computer science theory. Computer scientists, you will not find a chapter in a computer science textbook on something like bit ratio. You will find them on circuits. It's actually a huge field, what's called circuit complexity theory. Here is, in a certain sense, is one, not the most powerful by a long shot, but one of the most powerful ones. It's called a Turing machine. Do people here, anybody who does not know what a Turing machine is, raise your hand. Everybody knows what a Turing machine is? Okay. Anybody else? Okay. There are some brave souls who will admit to it. But so let me then just very, very quickly go over a Turing machine. It's very, very important because of the Church-Turing thesis, and this is not even provable. It's kind of like almost a definition, but it seems to be true, that any function that we would regard as being computable, including the function that's going on in your brain, is computable by some Turing machine. And as best we can tell, that actually is the case. So what is a Turing machine? It's actually very simple, very ugly, I have to say. But there it is. There are other machines which are equivalent to a Turing machine, which are far more intuitive, so far more beautiful, but it turns out they're harder to actually work with mathematically. So that's why people use Turing machines, like what are called recursive functions and things. So here's all that amounts to. You've got a, in general, an infinite string of bits called a tape. You've got what's called a head, which has only a finite number of internal states, one of which is called a halt state. But each time the head is located at some particular bit on the tape, that bit has some value. And so what happens in each iteration is based on the current state of the head and the bit that is currently reading. The head changes to some new state, writes a new bit at that location, and moves in either direction on the tape. There's a little deterministic rule that determines this for a Turing machine. The input is the initial bit string on the tape. The output, the computation ends, if ever, at a particular time that the halt state. When the head enters its halt state, that's it, computation over. And the associated computation is the map from that initial state to the state when it enters the halt state. That's it. In particular, not only your brain, but also, more important in a certain sense, the Python interpreter in your laptop can be viewed as a Turing machine. So everything, Turing machines. It's got some amazing properties. I would say that some of the deepest insights, the deepest philosophical theorems that humanity has ever come up with have to do with properties of Turing machines. It's like Gödel's incompleteness theorem. This is the deep shit. This is the stuff that makes us humans realize, oh, you silly children, you don't know what's really important. Here are just a couple of a very, very simple one. This is not as deep as the others, but it's very, very easy to prove that almost all binary valued functions over bit strings. So this is not a circuit that's only a given size n. The input can be of arbitrary length. Almost every binary valued function cannot be computed by any Turing machine. And I mean almost every in the sense of measure theory. So in the case of U, that means that almost every function that can be written down from the Booleans, from the Cantor set over Booleans to a bit, you cannot compute it. So anyway, cute little fact. So people may have heard of Kolmogorov. He's another one of these aliens, or maybe he's both an alien and from the far future, both, who knows. But anyway, one of the things he did in his idle moments, sitting in the bathtub one day, he came up with a definition of what we now call Kolmogorov complexity. And it's a way of measuring how complex a system is. Back when, in terms of, assuming that it can actually be modeled as a bit string, some finite bit string. And what it says is that the complexity of, for example, the first 1,000 digits of pi, the complexity of it is given by the smallest computer program I can feed into a Turing machine, such that that computer program will compute the first 1,000 digits of pi. Okay? By this definition, actually, the first 1,000,000 digits of pi has far less complexity than just a purely random number that's generated by, say, a Geiger counter. But that's what's called Kolmogorov complexity. It's concerning this that you run into some of the really deep stuff. And it's related to Shannon entropy. You can show that in the limit of arbitrary long strings, the two are the same thing. It's also uncomputable, meaning that you can prove that no computer program can actually be given any desired output of a computer and calculate what the smallest program is that would give it. So in general, maybe not for the first 1,000,000 digits of pi, but in general, there are many, many strings where if I ask you, what is the smallest program into your Python interpreter that can actually generate that set of strings, no Turing machine can compute that. In particular, you cannot compute that. There is some minimal, it's easier to find it, but you and anything that we can ever construct will never be able to actually give you that value, what the length of the smallest program is. Okay, so I keep going on about, well, we don't need to get into this, certainly in the interest of time. I keep going on about how beautiful it is, profound, all these impossibility results, a measure of complexity, but in a certain sense, it's all aesthetics. You can sort of adopt the physicist's criticism of philosophy of, well, that's beautiful, that's great, and enjoyable in the bathtub, but what's the actual practical importance? Well, we can take that to heart and say, let me actually instead consider a thermodynamic version of Kolmogorov complexity. So in the thermodynamic version, rather than saying I want to find out for the first 1,000,000 digits of pi, what is the smallest computer program? What is the size of the smallest computer program that would compute those first 1,000,000 digits? That's just Kolmogorov complexity, that minimal size. Instead, ask what is the minimal amount of entropy flow that would be generated by running any Turing machine that would generate the first 1,000,000 digits of pi. Okay, a priori, it might not be the actual minimal program that results in the minimal entropy flow, and in fact, that's in general true. So if you calculate that, it takes about a couple of pages of algebra. What you find is something that can be viewed as a correction term to Kolmogorov complexity to make it be relevant to physical considerations like thermodynamics. The minimal heat flow for any given distribution, for any given desired output to compute V is given by the Kolmogorov complexity plus two correction terms. This one, Z, that's a normalization constant, a partition function. It's known as Chaitin's constant. It itself is an amazing beast. It's one real number, and buried in that real number is actually the solution to every single mathematical question that you can pose. It's given by some bit somewhere in the in Chaitin's constant, but that's a whole nother talk. And then this log of G of E, that is the total probability of any particular input string actually ending up computing V. So it's a correction to Kolmogorov complexity. All those deep theorems I said before concerning Kolmogorov complexity, we can now try to go after them for thermodynamic Kolmogorov complexity instead. We've done a little bit of it. And here are some of the kinds of results. Kolmogorov complexity is unbounded. There is no value 73 such that it's going to be the case that all possible output strings that you want to compute, their Kolmogorov complexity is less than 73. You just keep generating larger and larger output strings, you will find one whose Kolmogorov complexity is greater than 73. You can't ever find it, but you know that it must exist. In contrast, the minimal heat flow, the thermodynamic Kolmogorov complexity, actually has an upper bound. So even though the minimal Python program, there is no upper limits to the size of the minimal Python program that will do any computation you want. You need a larger and larger program to compute it. There is an upper bound to how much heat you must generate in computing that particular desired output. And this is not easy to prove, but you can actually prove that. In the interest of time, let me go through all of that. All kinds of questions that nobody's even started to look at the answers to concerning thermodynamics of Turing machines. And in particular, all that profound stuff that I was talking about, nobody knows. Okay, now in the last little bit, when should I sort of aim to end? In 10 minutes or something? But something like that? Okay. So let me now go to some work that is, that's being done right now. These are projects that we don't have the final versions of the paper, though most of it's on archive. First, let me go back to this simple formula. Landauer's bound is all about if delta sigma, if the entropy production term is 0, that's its minimal possible value. What does that give us for the negative delta Q, the entropy flow for the particular system I'm interested in? Is that actually what's important though in the real world? On the scale of humans, like our brains, these computers, anything that we might actually come across when we're analyzing complex systems, is it really the Landauer's bound? Because the Landauer's bound is the drop in entropy, and it's being multiplied times KT. KT is a real small number. If you just look it up, what is K and what is T, multiply them together, how much is this energy? It's really, really small by many orders of magnitude. This right here is generating on the order of 7 to 8 times KT per logical operation. So, sorry, 10 to the 7 or 8 times. 7 or 8 orders of magnitude more heat than just KT. And moreover, if you've got a system that's in what's called a non-equilibrium steady state, delta S is actually 0. The entropy is not even changing, but it's still generating heat. So what is actually important for analyzing complex systems like computers? Arguably, interesting as the Landauer cost is, as easy it is to work with, the generalized Landauer cost entropy flow, what's really important is delta sigma. That is what is dominant. It's dominant even down at the level of like microbiology. There's a paper I did with a fellow called Chris Kempis. We analyzed the ribosome in a cell as a computer. And we found that it actually gets to, it's amazing how good a job evolution has done. Its cost, its energetic cost, which you can measure in terms of ATPs and so on, is on the order of 4 orders of magnitude worse than the Landauer's bound. This is on the order of 7 or 8 orders of magnitude worse. So every single one of you has ribosomes that are just mapping your DNA into proteins, that viewing that map as a computation is many orders of magnitude more efficient than this. That's like a genetic algorithm at work where the cost is energy. But in any case, the obvious question, though, is why is delta sigma so big? Why was nature not able to get the ribosome to have a delta sigma much, much smaller? Why has it got to be producing 4 orders of magnitude more delta sigma than the change in entropy? For that matter, the minimal value is 0. Why can't it get closer? What is it that determines delta sigma in the real world? It's all about the constraints. Mother or father nature, as the case might be, who is working in natural selection, they have to work with organic chemistry. Organic chemistry is messy as hell. The engineers who are doing this, they've had to work with CMOS. There are all kinds of constraints on what you can do in terms of the rate matrices and so on with organic chemistry or with CMOS. Those are all contributing to delta sigma. So the obvious question is are there broadly applicable non-negative lower bounds on the entropy production to complement Landauer's bound? And there are. And so I'm going to talk about a little bit now. I'm going to focus on 2 very, very briefly. One of them is called the speed limit theorem, and one of them is called mismatch cost. And I will show a little bit about how you can look at these 2 lower bounds on EP and use them to say something about the thermodynamic resource costs of computational machines, in addition to what I've shown up to now, which all has to do with the entropy flow. Okay, the original speed limit theorem. The reason these are called speed limit theorems, think about computation. Or think about that matter, just bit erasure. I can actually erase a bit in the form of a piston, quasi-statically slowly, so it's going to be thermodynamically reversible the entire way. So I'm just erasing a bit. You've got, say, in the piston, you can compress it all the way down or let it be out, and those are the 2 states of my bit. And so erasure, I do it quasi-statically slowly. It's at all moments thermodynamically reversible. There is no EP. Okay. Why can I not design a computer that uses those kinds of things? Why could not ribosomes work quasi-statically slowly like that? The reason is because you're never in the real world have an infinite amount of time to do a computation. If I see a tiger coming in that room, that door, I've got to do a computation very, very fast, or as the joke goes, I get weeded out of the gene pool. There are constraints in terms of time. And it turns out, these are called the thermodynamic speed limit theorems. It turns out that the minimal amount of time you have to run a process, that actually provides entropy production, a lower bound on entropy production. The smaller the amount of time you have, the greater the lower bound on EP. The lower bound is no longer 0, it's now greater than that. For example, here is the original form of the speed limit theorem. L is actually just the L1 distance. It's the absolute value of the distance between your initial distribution of your system and the ending distribution. And A is basically a way of measuring, it's a clock, it's a way of measuring time. And if I'm going to be sending a distribution from a state P0 to a state P1 by whatever process, then the minimal entropy production is lower bounded by that distance between the 2 distributions. This actually falls out as properties of continuous time Markov chains. It's amazing the properties of these things. There's so much that's still being discovered. It's not like continuous time Markov chains. The math of them was all known a century ago. No, nothing close to it. Okay, so let's now take that and just apply it to two different circuits. Say that each gate takes the same amount of time to run. Apply the speed limit theorem for a particular distribution and find out which the bound given by the speed limit theorem. Remember, it's only a lower bound, so it could be weak or strong, but nonetheless, that lower bound, it's going to in general vary with the error rate of the gates. As I change the error rate of the gates, I'm going to be changing P0 and P1 a little bit. So let's take two circuits. These ones are logically equivalent. They're both mapping the 3 bits A, B, and C to this is the logical AND of A and B, that's the logical AND of A and C, and this is the OR of them. They're both doing that. Let's just see how the speed limit theorem bound varies between these two gates as we vary the error rate of the gates. Here's what you get. For certain, if you get up to the level of perfect gates, then there's multiple ways of actually computing the underlying system that's being evolved. That's what BaseNet versus global means. But basically, you'll notice that the this green curve up there, circuit B BaseNet is above circuit A BaseNet, and if we model the circuit in a different way, it's called globally, then you get the circuit A global is actually now less than the circuit A bound for circuit B bound for global, and there's crossover points. What causes these curves to have these shapes? What are the curves for other circuits? We don't know. This is all completely new stuff to be done. So before I was saying it's completely open to figure out which of two circuits that implement the same function have the minimal Landauer bound, the minimal amount of heat flow. This is saying, well, but if I want to implement them in finite time, which of them has the minimal entropy production on top of the drop in entropy, which is the Landauer bound? Again, more open questions that nobody knows the answer to them. And then finally, I'll talk just a little bit about what's called mismatch cost. It's actually central to the paper that Edgar and Gonzalo and I are working on right now. Let's go back to something that I like, bit erasure. So here's a context. It turns out sociologically, very, very strange. If you look in statistical physics textbooks, both conventional statistical physics and stochastic thermodynamics, all of the problems are going to have the following form. I'm giving you some particular initial distribution over states of your system. And now as you vary parameters in the system, how does that affect the thermodynamic costs? That's what everybody's been focusing on. That is backwards for almost every problem a real engineer faces, which is, I've now constructed my system. Its initial states are set by the random distribution of David, whatever he puts in here. If I loan this to Gonzalo, it's a different, same system, but different initial distribution. If I take some cell, like a paramecium, its initial states, let's say, are determined by what it detects in terms of the chemicals in a particular pond. I take that exact same paramecium and put it in a different pond. It's now the same physical system, the same dynamics, but a different initial distribution. And this is exactly the problem we were talking about for the AND gate. The exact same AND gate giving it different initial distributions. Okay, so what? That can't have any importance. Turns out it does. Take some particular system, and let's assume that there is some initial distribution for which there's 0 EP. This makes the algebra easier. I could do it, makes the notation simpler. I could run it through where we don't make this assumption, but let's just make this now for notational purposes. So for some Q0, this system, whatever it is, I don't care how it works, has 0 EP. Now run it with a different initial distribution. And this works not only, by the way, for countable state spaces evolving according to a CTMC, it holds for Langevin dynamics, it holds for quantum systems, it holds for systems undergoing deterministic dynamics. What I'm going to be showing you is extraordinarily general. If I run that exact same physical process, the exact same P of x1 given x0, for a distribution P0 rather than Q0, then the minimal EP, this is an exact equality, not an inequality, it equals the relative entropy, the KL divergence between that P0 and the original one, minus the KL divergence of both of them evolved according to this exact same physical system, P of x1 given x0. In general, what's called the chain rule of relative entropy, you can use it to, or rather data processing inequality of relative entropy, you can use to prove that this is greater than or equal to 0. So the exact same physical system with a different distribution, you're now going to have a greater entropy production than you did before, and it almost doesn't matter on the physics of that system that is causing this. Okay? So here's a simple example involving bits, and I'll just present this and stop in the interest of time so that people can see, you can get, hopefully you'll get an idea of the power of this for considering more general things like circuits. Let's, this is called the mismatch cost, this drop in KL divergence. Let's consider a, oh, okay, go right through that. Yes, here's the example. Let's take two bit erasing gates, two pistons. Each of them run by itself is thermodynamically reversible, 0 EP. Fine, I've got two thermodynamically reversible bit erasers. I now run them in parallel. What is the minimal EP now? Well, if their initial distributions are statistically independent, now you would still have 0 EP. But if their initial states are statistically coupled, so that the initial state of bit 0 tells me something about the initial state of bit 1, and now I run those two parallel bit erasures, now it is going to be, the overall system will not be thermodynamically reversible. The mismatch cost formula, you can use that to derive the minimal drop in relative entropy. It's non-zero. It's actually equal to the change in mutual information. Running two thermodynamically reversible gates in parallel, it loses the information in the initial coupling. You end up erased and erased. So I've lost the information that was statistically coupling them, information theoretically speaking. That causes this to have non-zero entropy production. It's got thermodynamic consequences. You're going to drain your battery more than you would otherwise. Modularity increases entropy production. Modular systems, when you design circuits, when Mother Nature designed the genes in your head, modularity is all over the place. It has great engineering benefits in terms of robustness, in terms of evolvability, all kinds of things. But whatever other its practical benefits might be, it is thermodynamically costly. So again, obvious problems. Here is a Boolean function that I want to implement, and here is how much modularity increases EP. But if I go more modular, I'm going to actually then have things like robustness against component failure and things like that. How modular should I make my circuit now? So I will end it there to give people at least a little bit of time to go through questions. This stuff here was all about applying that mismatch cost formula to circuits. These are the two circuits that, again, the same ones we had before, that implement the exact same function, but they have different kinds of modularity, so to speak. And so the end result is that they actually have different mismatch costs. So we've got now a problem of, for a given Boolean function, one optimization problem is what is the Boolean function that actually minimizes generalized Landauer costs, the drop in entropy. Here's another one, is which is the one that actually minimizes the mismatch cost. Nobody knows why. I'll whip through all of this, and just to get it up into YouTube, here is a bit of a bibliography, so people can all take these down later. This is now several years out of date, but people might still find it interesting to run through some of this. Okay, and that's all. I'll end it there. Thank you very much.
Maybe we don't hear it, but it's probably yeah, yeah. But anyway, someone for question. What do you mean by modularity?
So for example, if you were to look at an actual real circuit board, if you've ever seen just photographs, or if you want to sacrifice your computer in the name of science, or you want to crack it open, what you will find is it's like fleas upon fleas upon fleas. The overall circuit board has many different chips, and if you look, and so those are modular. They have many more connections in between the elements of such a chip than between different chips. So there's many more intra connections than interconnections. And moreover, it's hierarchical. If you then look within any single one of those chips, you will find that same kind of thing, that the number of connections within is much greater than the number of connections without. And that's modularity.
We have a kind of measurement for modularity.
Oh, there are many of them in the literature.
And they are connected this much cost with the measurement of modularity.
That's the intuition. Has anybody actually even tried to analyze the mismatch cost for these different definitions of modularity? Not yet. Well, you get to hold it, make you feel good.
One is more technical. When you define or you show the specific theorem. If you go back to the boundary, I don't know.
Yeah, so this is going back quite a way. Ding, 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 ding.
Yes.
Yeah.
So I understand because you say here that A is stochastic, so this bound is over realizations, or is
that's all those statistical physics. Think about it. This is a interesting point. All of statistical physics and stochastic thermodynamics, everything, it's about the dynamics of probability distributions or of density matrices if you're talking quantum. It's not the same thing as the dynamics of a single state. So to be able to even talk about any kinds of thermodynamic costs of any sort, any kind of thermodynamics, you must specify an initial distribution over all the variables. And so that is being specified here. And the map from P0, strictly speaking, this is the initial distribution over all of the gates in the system. That's your full system. So you're mapping that to an ending distribution.
And then the second thing is that you say that there's room for applying this kind of ideas to many far from equilibrium systems. And for me, there is always a difficulty of how, I mean, for sure, I can compute the entropy production for any.
So entropy production by itself one way to view it is as a measure of the irreversibility. Because if you go back to the actual you can write down its definition in terms of rate matrices. And basically, if on average, that you generate trajectories whose time reverse is very, very rare, that is a measure of the entropy production. So when you're at equilibrium, going forwards or backwards at a trajectory level, not just at a distribution level, it's about the same probability. Entropy production is when those are asymmetric. So you can use it to measure the irreversibility of many processes. But also, there are many stochastic thermodynamic theorems that are being generated these days that don't involve entropy production, that don't even involve energy explicitly. It's all properties of continuous time Markov chains. And even the ones that do involve entropy production, it's actually, this doesn't work in most cases, but there are at least a few where you can use them in conjunction with one another. So one theorem will say, okay, here is a lower bound on the entropy production, but then that entropy production is an upper bound on this. So therefore, you can just use transitivity to get relationships between two quantities, neither of which involves entropy production. So you're correct that many of the theorems you cannot apply, but many of them, without just viewing it as irreversibility, which is very often interesting. But many of the other ones you can apply even without worrying about entropy production or energy of any sort.
Question is somehow related, but it's not exactly the same. For example, this take this where temperature was important and when was not. You are applying this non-equilibrium stuff, so physical there is no single temperature defined, but entropy production has units of energy.
No, entropy production has just units of no units. It's entropy, just like entropy has no units. I should have, I guess, clarified this. In almost everything that I've been presenting here, what's standard in the literature is you assume a single heat bath rather than multiple ones, and you just set KT equal to 1.
So I missed the temperature was not there. So
yeah. So that's what I mean. KT equals 1.
Physically, so is this independent of any temperature? The same.
No, there's going to be to get that delta sigma to be related to heat flow, you multiply it times KT.
But then this is a single temperature.
Yeah, and you can do similar things when there's multiple baths with multiple temperatures. To be honest, much less of the literature that's out there, that's known, that's very central to a lot of what's done. But the vast majority of stuff like speed limit theorems has not been extended to that. It can be, but it just hasn't. It makes a lot of the equations more messy and so on and so forth. But if one wanted to, one could do it. Sorry? Oh, there are different speed limit theorems. We were in these calculations actually using one that recently appeared in PRL by Lee and a bunch of others. In some situations, it's actually very far from saturation. I don't know that there's any simple intuition. People obviously in their papers where they work examples through, very often you can also calculate what the exact EP is, and so you just confirm that yes, the bound works. And people do worry about how closely they are saturated, but I don't think there's any general lessons about that are currently known.
Question? I have a question related with the input model.
kind of difficulty to understand the connection between the entropy production and the heat produced by a computer or something. Is there any justification to you can connect the Shannon information entropy with the thermodynamics?
Yeah, so when you can show, remember I mentioned very briefly, I actually talked about this. I said local detailed balance very briefly, and I emphasized that this is that this was all mathematics. Where was it? Yeah, right here. That this was all mathematics, and you need to put a little bit more into it to make it be physics. Like I could write down the mathematics of, say, Lorentz transformations and so on, but it doesn't mean anything until you say, oh, and this variable, by the way, is space, that one is time, and this one is speed in your little frame. You've got to give some interpretation. Or you need to actually, I mean, in that case, it's simple, but here, what one does is you assume, let's say that the reason my system is undergoing a continuous time Markov chain, rather than just Hamiltonian dynamics, unitary dynamics, is because it is coupled to an infinite heat bath. Okay, so that heat bath, information goes in, no information comes out. We're assuming it's always at thermodynamic equilibrium. And there's lots of complicated things that people have sort of verified that that's actually a fully formally legitimate thing. Let's just assume that. So then if you also assume there's what's called micro reversibility, meaning that just normal time reversal, your time reversal symmetry down at the microscopic scale, then basically for the case of a single bath, that amounts to assuming you've got detailed balance. Okay, so detailed balance is saying the changes in the Hamiltonian and the probability ratios going forward and backward. Here's how it's related to the ratio of the temperatures. You can apply that here because you know about the probabilities going forward and backward via the continuous time Markov chain. And basically what comes out at the end of the day is that you've got this KT that gets multiplied times the delta S. That's why I did it up here. So this is the general formula. For this to actually be a heat flow, you've got to basically multiply everybody times KT. So when you actually try to just take these general things and say, I want a continuous time Markov chain, let me come up with a physical model of a system that's undergoing a continuous time Markov chain because of its interactions with a heat bath. What you will find is in all of those models, this quantity, which is this one right here, that one is actually involves a temperature term, KT, to get it to have to do with the heat flow rather than the entropy flow rate. That's many, many steps, and it's kind of more messy, and that's why I didn't want to get into it. Okay.
So I posted, we thank David again.
Okay.
And right, this should be 4 p.m. Unexpected.